Hey there, welcome back to Short Takes 331. Today we continue our discussion of machine learning and we're going to talk about something called backpropagation. So over the last couple of videos we started talking about machine learning and we're thinking then of a neural network as something that looks like this. So a neural network basically is a kind of function where there's an input, it goes through a series of layers of neurons, of artificial neurons, and the information is fed forward all the way to what we call an output layer, and then you have the output of the function. And this is what we call a typical feed-forward neural network. And ultimately, like I was saying, it's a function that is designed in a particular way. So here we have these neurons that are organized in layers, and we have, for each neuron, we're going to have weights and biases. So each neuron is going to have a bunch of weights associated with the various inputs of the vector x, and there's going to be a bias for each neuron, and the same for each layer. And there's going to be activation functions as well, which we need to decide which form. Those could vary from layer to layer. They will vary depending on the architecture that you decide on for the network. And these parameters, the weights and the biases, are what are going to effectively do the learning. So we're going to fit these weights and the biases so that the input x matches a desired output on the output layer. And that is fixed by some data and by some cost functions. So we're going to define a cost function, which is what we need to minimize. And usually we do that by a stochastic gradient descent. In other words, somebody gives us some data, which is given here. As an example, we have pairs of input-output that we know are what we want to match. They go from 1 to n. N typically would be very, very, very large. Ideally, you want a lot of data. And so what you want to do is you want to make sure that given an input, the parameters are set up so that you reproduce the desired output with your network. And that's why you have to then tune these parameters, the weights and the biases. So here, by the way, I just used W and B here generically to denote that there will be weights and biases associated with each layer, but of course they're not the same from layer to layer. Usually the cost function will take a form that looks like this. It will be a sum over cost functions associated with each sample. So in other words, a deviation for a given sample is added together with the weights, with the deviations from other samples, and then together, all that sum together gives you the full cost function for the whole network. And an example of that is given here. So it could be that you decide that the cost function for a given sample is given by this. It's the difference squared between the desired output, what you want to get, and what the network gives you. Now, regardless of how you choose this cost function, it could be like this, very simple. It could be more complicated, like the logarithmic case we saw in the previous video. But regardless of that, we need the gradient. So if we're going to use stochastic gradient descent, then we're going to need the gradient of the c sub I, of the cost functions. So let's see how we're going to do that. And this could be fairly complicated, as you will see here. So if we want the change in the cost function, and so here I will omit the term I, the index I. But if you want the change in that function with respect to a weight on a given neuron for a given input index and on a given layer, then you have a complicated situation. You have to sum over all possible outputs of the network because the C, this function C, will depend, as you see in this example here, on the outputs of the network. The outputs will depend on the inputs in a complicated way through a chain of weights and activation functions. And so this part is going to be completely given by the cost function and the network output. But this here is going to be more complicated depending on how deep into the network you need to go, depending on which derivative you're interested in taking. You can see why here. So this is the output of the network, and then the output of that output is given by a function evaluated at another function, and so on. This is a sequence of nested functions. And here you see what happens in the first two layers. You have the function of z2, where z2 is this argument of our function. This is on the second layer now. And there's a second layer weight, there's a second layer bias, and then you have as an input to the second layer the output of the first layer, which is z1. So this is the first layer activation, z1, and it's given by the weight of the first layer, the input vector and the bias of the first layer. So you see, this could be very complicated, especially if your network is very deep. So we're not going to tackle this fully. This could be done if you want algebraically, or it could be done with indices, and it involves just keeping track of all the indices very carefully, but it doesn't help very much to that if you want to fix ideas. So what I want to do here is to work out two very simple cases. So the obvious first case that we want to tackle is the case where the network is this. So there's basically no network. It's just a single neuron. There's an input, there's an output given by this activation function, and our z is as usual wx plus b. So x again is the input, and w and b are the weight and the bias of this one neuron. And so our cost function will be a function of a, of the output. A in turn will be a function of w. And so if we want dc dw, then we have to account for the fact that c depends on a depends on w, and a depends on w in this way, through the activation function, which is itself a function of z, and z is this very simple linear combination, which of course, in general, z will be a vector, which is the output of matrix multiplication of w with x plus another vector b, and so on. It's much more complicated in the general case, but here we're keeping it simple just to fix the ideas. And so what you get is this chain then of multiplications, which later will be matrix vector multiplications together with Hadamard or point multiplications, pointwise multiplications. You have to be careful about that in the more general case. But once again, to fix ideas, we work out the simple case, and this is what you get. You get dcdw is dcda times dadw. So we're just using the chain rule. And dcda is basically completely fixed by the form of the cost function you want to use. If you want to use something as simple as the quadratic form given here, then basically the dependence of c on a is just quadratic, and so we all know how to take that derivative dcda. Now dadw will depend on how a depends on w, and so that's given by the activation function df/dz. And then finally we get dz dw, which in this case, where you have just a single neuron, is just x. Okay, and that's all there is. And so once again we get dcda dadw, and so dcda df/dz dz dw, and finally we get x here. And so you see, this is independent. We will always have this because it depends only on the form of the activation function, rather the form of the cost function, and how it depends on the output layer. But then here is where we are going to be working a little bit more. And so here the f/dz is fully determined by the activation function, and it will be evaluated at z equals wx plus b. So we're going to need the values of the activation function at each layer in more complicated cases. And so here's a slightly more complicated case that's more meaningful. What happens if we have two layers? So now this is what it looks like. So we have here a function a of w, where now this final layer activation is the activation function evaluated at the z2, which is taking into account the weight of the second layer, and the output, the activation of the first layer, given by this function here, f of z1, where z1 is w1x plus b, and then again z2 is that whole combination plus u. So I use a different letter here for the weight, for the bias of the second layer, just to differentiate that from b. So I want these to be a little different. I'm going to be focusing on the weights, but of course in real life you will need derivatives with respect to w's, and also derivatives with respect to b and u. But basically this is what you would have if you have this simple geometry here, this simple design for your network. This is hardly a complicated network at all. Of course, one would say it's hardly a network even, but you do have an input, and you have a weight and a bias, another weight, another bias, and then the output of the network is just this one number a. And so to tune, if we were to tune this network, then we would need dcdw2. We're going to need the gradient with respect to the weight of this second neuron here. And once again, that's given by dcda dadw2. As we were saying before, dcda is going to be always tagging along for the ride. It depends on the form of the cost function and nothing else. Of course, this will be evaluated at the output of the network. But other than that, this is where the complication enters. So dadw2 is then the change of A with W2. And so that's encoded in here. And so the W2 is going to be given by this chain rule. So we have the change of F with respect to its argument, Z2. So the change of this F with respect to Z2, and then the change of Z2 with respect to W2. And so this, the FTZ2 is fully determined by layer 2, and or rather by function evaluated at Z of 2. Of course, Z of 2 or Z2 will depend on everything else that happens in the network, but this is basically given if you know the output of the network at this layer, then after layer 1, then you have this information, and so you could just evaluate the FTZ2 right away, and then dZ2 dW2 is just F of Z1. So if you look here, the change in Z2 with respect to W2 is just this F and nothing else, so F of Z1. And at that point, we would be done. And so the output, or rather the full expression for the change of the cost function with respect to the second weight is just dCdA, again, that's always along for the right, and then dF dZ2 times F of Z1. And notice here how we have not only this derivative of the activation function with respect to Z2, but also the layer, or rather the activation function of the previous layer. Okay, and so this starts to tell you how these things get multiplied and how this could be very small, and it could affect then the gradient of the next layer of W2. So the activation function evaluated at Z1, this is what you see here, the function evaluated at Z1, is going to be the input into the next layer, so the input of this layer into this layer, and that will affect how this gradient behaves. And therefore the choice of activation function will enter here and will also enter here. What happens if you go deeper into the layer? So notice how we're going backwards here, and that's why it really is called backpropagation. So we're going here, we just calculated this, and now we're going to look at this, and you'll see more precisely why this is called backpropagation. So if you try to calculate the gradient of the cost function with respect to the weight of the first neuron, then you have once again dCdA, dAdW1, just using the chain rule, and dCdA, once again, it's along for the right, and the dAdW1 we calculate here. So the dAdW1 is dF dZ2, dZ2 dW1. Let's go and take a look. So we're trying to calculate the change of A now with respect to W1, and so we have to go in here and calculate the change of F with respect to Z2, the change of Z2 with respect to W1. And so that's what we're doing here, Z2 with respect to W1. And so now we look at the change of Z2 with respect to W1. And if you look at the formula, then you see that that's W2 times dF dZ1 and then dZ1 dW1. And so we have this dependence, this linear dependence of Z on W2 and on Z1 rather. So we can look at that here. So we have, if we take the derivative of Z2 with respect to W1, then Z2 depends linearly on W2 and on this F here. And so the derivative of Z2 with respect to W1 will have this factor, and then the derivative of F with respect to W1. And so that's what we have here. The derivative of F with respect to W1 is then dF dZ1, dZ1 dW1. And finally, dZ1 dW1 is just X. So if we go back up here, the derivative of Z1 with respect to W1 is just X, because Z1 is just linear in W and X, and of course B, but this vanishes because we're taking a derivative of Z1 with respect to W1. And so putting it all together, then we get dCA, dCdA times dF dZ2 coming from here, and then this product, this factor here, dZ2 dW1, becomes W2 times dF dZ1 times X from here. And so once again, notice how we get the input into that particular layer to play a role into the derivative. And so if that input is very large or very small, it will play a role. And we also have the derivative of the activation function at that layer. And then we have the weight of the next layer and the derivative of the activation function at the next layer, and so on and so forth. And so you see how then the fact that we're trying to see the change of the cost function with respect to the output at the very end of the layer, then you get this chain of factors that go from what happens at the very end of the network all the way to the beginning of the network. And this pattern repeats itself if you have deeper networks, of course, and more complicated architectures. And so you always have this first factor along for the right here taking a derivative with respect to a weight at the very end of the network and here at the very beginning. And then you have the FDZ2. Here we also have the FDZ2. And here the calculation ends here with the function, or rather the input into the last layer, which is the activation function of the first layer. And then here you have another factor, and then the input into that particular layer. And so this pattern, once again, repeats itself. It continues on and on and on. And the gist of it, the gist of backpropagation is really here. Is really that we perform far fewer operations if we calculate starting at the last layer. So to calculate the gradient, then the best idea is to start from the end. You start at the last layer, it's like we did here. We start at the last layer and you calculate this part, and then you multiply by this and you get the result you want. But if you save this result, then you can use it here to calculate the next layer over. And these factors will repeat themselves, and you would continue to multiply by the input into that layer. And if you had more layers, then you would have a factor like this and another factor like that, and eventually an x at the very end. And so we use then these intermediate steps in our calculation to calculate the gradient of the previous layers, and so on and so forth. And so we start at the last layer and we move backwards from there, and that's why it's called backpropagation. If we were to do forward propagation, imagine if we were to calculate this first, then all these results would basically be calculated once, and you will have this answer, and then now you're going to need this. So well, that's been by the time you want to access that, then it's already used into all this stuff. So you have to recalculate all this stuff to reuse it here, and so that's not a good idea. So the best way to proceed is then to go backwards. So you use this, and then you accumulate the next product and to calculate the next layer, and then you keep accumulating those results into a big product until you get to the first layer. And that's how you calculate all the way to the gradient on the first layer. And that's it. That's about all I have for you today. That's the gist of backpropagation. In practice, of course, this is coded and already done for you in multiple routines that you can find on the web. So we're not going to worry about coding this, but this is how you can see that the architecture of the network enters into the derivatives of the function into the gradient. And that's important because learning will depend a lot on the behavior of those gradients. Once again, that's all I have for you today. I hope you find this useful and interesting and instructive in some way. If you did, please consider liking and subscribing to the channel, and I will see you next time.